Welcome this evening to the 52nd Presidential Address of the Royal Society of Tropical Medicine and Hygiene. And our topic tonight is mapping the future of infectious diseases of the tropics. So this overview slide helps you understand, and we'll come back to this throughout the talk. It helps us navigate where we're going. And I'm going to spend the first 10 minutes, because we are a very diverse audience today, talking a little bit about the history of the Royal Society of Tropical Medicine and Hygiene and some of the things that we do today, and a little bit about what I hope to achieve with the Society over the next 2 years as its president. We'll then talk so that you can understand a little bit more the sort of context of what we do, both as a society and myself and my lab as researchers, about the global burden of disease and particularly how that affects the tropics. We'll then move on to talk very specifically about what we do in our group, and the first thing that we'll do, like all good scientists and all good builders, is criticise what people have done in the past, and then we'll go on to how we do cartography today, and we'll probably spend most of the time talking about that, so mapping the present. We'll then talk about how we'll scale up what we're doing, look a bit about some of the things that we might need to worry about in the future, and then we'll make some conclusions and go and have some drinks. So, history. The Royal Society of Tropical Medicine and Hygiene was founded in 1907. It was designated a Royal Society in 1920, and its current patron is Her Majesty Queen Elizabeth II. It's been going for 106 years, so the more numerate among you will work out that it's had 51 presidents, 2 of whom have served 2 terms. 51 of our presidents have been white, 50 have been male, and 46 have been medically qualified. They have an absolute constellation of academic, civil and military honours that are a bit too numerous to document. The median age to inauguration of presidency is 62. So I have the honour of being the 52nd president and not quite its oldest. The motto of the Society is Guardians of the Torrid Zone, or Protectors of the Tropics. So I think you'll get the impression from this that we're very established as a society, but historically we've also been very establishment, and that's one of the things that we'll talk about moving forward. So in preparing for my presidential address, in my obsessive-compulsive way, I first read, in fact, what every one of the other presidents had said preceding me, and 44 of those have indeed been published, and the rest of them I managed to nag other presidents to get. So in doing that, it was actually quite difficult to trace some of these. So Jerry and I have put together a small article today, and we've made all of the historical presidential addresses open access, so anybody can have a look at them. And I do this also to sort of forgive the cursory treatment I'm going to give tonight of the history of the Society. It's a really illustrious one, and it does bear having a look at. It's an absolute who's who of tropical medicine, and I'll just show you some of the past presidents here. You've already seen Manson and Ross, and we'll talk about those a little bit in a moment. And you can see this kind of echoes the idea of established and establishment. You'll see the presidential necklace that I'm sporting here goes through several iterations as we move forward. For those of you that know anything about tropical medicine, this is an absolute who's who of who contributed to the development of the discipline over the last 100 years. Many malariologists that are extremely well known to me, but many people in this list would be eponymous for many of the diseases that we're still worried about: brucellosis, leishmaniasis, etc. We're almost there. We move to the more colourful and the more smiling presidents of recent times, and 3 of the last ones are in the audience today. I can't really do justice to the history of the Society, but I will essentially just talk about 2 of the past presidents. So Sir Patrick Manson was our first president. He discovered the role of mosquitoes in the transmission of filarial worms with some experiments that would never pass any kind of ethical approval today. He was also the founder of the London School of Tropical Medicine, and I will repeat for you here The first inaugural address of the Society and the first paragraph ever written, and I will recapitulate this here. So I trust that it does not augur badly for the success of the Society that its first president has to commence with an apology. Such, unfortunately, is the case. I intended to devote some time to preparation, but having been called upon unexpectedly to take part in something else, I apologise in advance that I wasn't able to prepare, and trust you will be indulgent to my shortcomings. I'm afraid my neurosis for this occasion was such that if there are any shortcomings, which I'm sure there will be, they won't be through a lack of preparation. Perhaps our most famous president was the second one, Sir Ronald Ross, and he discovered the life cycle of avian malaria. He also received the Nobel Prize in Physiology and Medicine in 1902 for this work, and incidentally he was the first Briton ever to receive the prize. He's also of interest to me because he is an infectious disease modeller, and that's something that I've dabbled in a little bit in the past. And moving on now from the history, so if you'll let me, it is an illustrious history, but we're going to move on and talk about the Society today. So our charitable objects, and for those of you who don't know about charitable law, which I've been finding out a lot about this year, it's essentially the mandate of the Society. What do we exist for? And it's to promote the health and advance the study of the control and prevention of diseases in man and other animals. And that's a bit of, so I'll move on to that in a second. I don't think that's so well known. And it's to do with those diseases in the tropics and disadvantaged communities around the world. We have, after a recent governance review, a very strong structure. So Jerry McHugh is our chief executive. Our immediate past president was Professor Winstanley. We have 12 trustees, 9 of which are elected from the fellowship, and 3 of whom we draft in for additional skills such as financing. We formally welcome 3 new trustees today, Peter Horby, Dr. Van den Broek and Dr. Desabi. And we also formally welcome our new Vice President, Dr. Simon Cathcart, who's a long-time serving trustee and member of the Society. Our fellowship numbers over 1,000 in 89 different countries, and you'll see potentially something else that I'd like to deal with over the next 2 years, is that we have quite a strong geographical bias in our membership. One of the things that we do as a society is arrange lots of meetings, and today we've had the annual Research in Progress, which is predominantly for young scientists, very stimulating meeting today. And I'll talk more about our kind of trademark meeting, our biennial. The next one is in Oxford in 2014, about this time next year, and I'll talk a little bit more about that later, as I will be hoping to get some support from many of the illustrious people in the audience today. We run 2 journals, the Transactions, monthly, launched in 1907, Transactions of the Royal Society of Tropical Medicine and Hygiene, and the more recent quarterly journal, International Health. We also give out lots of honours and awards, 5 of which are there on the slide today. I'm going to highlight just 2 of those. So we have the Manson Medal here. This is our most prestigious medal, and in 2013, for those of you who weren't here at our AGM, that goes to Professor David Molyneux in the audience, and that's our highest honour for contributions to tropical medicine. So well done, David. Our next, and also one of our oldest medals, is the Chalmers Medal, also for contributions to tropical medicine. We give this one out annually to someone under the age of 46, and today that went to Professor Joanne Webster. So what do I intend to do as president? Well, I want to reiterate the fact that, and in fact steal what Peter just said, there is a nervous system in the society that runs regardless of the president there. So I benefit from some extremely strong foundations, a constitutional restructuring, and very stable finances. And as a president of a society like this, that's a really nice thing to do. My main aim really is not to upset any of that and focus on the business of the society itself rather than its running. We're also a path in the society where we're coming to the end of one 5-year plan and Hence, it's a really good time to come in as president, because not only do I get the opportunity to influence the next 2 years, I do actually get the opportunity to influence with the trustees and the staff the next 5 years. Some of the things that I'm going to mention in the next 2 slides, things that I want to focus on, aren't particularly novel or exciting, but they are important to us. And one of the things that I think that we need to always strive to do better is improve our communication with the existing fellowship. And there are many things we've already started to try and improve that. And one of the things I'm particularly keen to do is advocate to and for a wider fellowship. So this comes back to this slightly establishment notion and reputation that the society has. So I hope after the next 2 years we'll be able to present a slide to you of our fellowship that is a bit more demographically and geographically diverse. One of the things I think the society perhaps hasn't batted as strongly as it may have done in the past years is international health and development policy, and I would like to think how collectively we could play more of a role in that. And one of the things as a steward, I do need to keep a very close eye on our key revenue generators. I come into this as a very lucky president. We've got buoyant finances. I certainly don't want to leave after 2 years having caused any problems there. And essentially one of the things that helps us improve or fulfill our charitable objects is our journal stock. These we need to keep an eye on. Our impact factor we want to improve, and we as a publishing society need to look about the impact that open access will have upon us. And for a society it's a double-edged sword for us, because it is a big revenue generator. So that's something that we'll have to think about moving forward. So we've done with the history, and I'm now going to move on to the talk in terms of the cartography, the work that we do ourselves. And I first want to talk about the global burden of disease, so that you perhaps have a bit more of a notion as to what we are contending with as a society, and some of the things that determine the priorities. So the global burden of disease study, very nicely reported at the end of December 2012, very useful for this particular presentation. So I've got updated numbers for 2010, which I can synthesize for you. So essentially the global burden of disease study, for those of you that don't know it, is a mortality and morbidity audit. So across the world we have about 53 million deaths each year, and what this study does is to allocate those to 235 different diseases and injuries, so that essentially we can have a top of the pops for diseases, so that we can work out which one contributes more to disease and death than any other. There are 2 components to burden of disease, and so this is death and disease, or mortality and morbidity, and we can put those together, and this is the only equation you'll get, and it's a fairly simple one, into one metric called a DALY, and I do need you to understand that. So it's a disability adjusted life year, and this has 2 components. It's years of life lost due to the mortality, so the mortality component, and the years lived with a disability, so the disability component. And if you put those both together as a single metric, you get a very good idea about the burden of disease in any location. And this is essentially what this massive study does. It gets all its data from vital registration, and vital registration is in any country. If you die, people will try to work out what you died of and record that somewhere. And as you might imagine, that's highly variable across the world about the level of diagnostic specificity and the rigor of the recording. But if you get enough information on that, and the global burden of disease study is a massive undertaking, you can start to classify these things by age, sex and geographical regions. And the causes are categorized into 3 main groups, which will also be important to us moving forward. So these are communicable, non-communicable and injuries. So communicable are those that we can transmit between each other, either directly or via a vector. Non-communicable are those that we cannot transmit between ourselves, such as a heart attack, and injuries are obviously road traffic accidents, self-harm, etc. And what we're going to do is take the results of this study and compare prospects of life in tropics and non-tropics. So to do that, this is your first map. So the Global Burden of Disease study defines 21 regions around the world, and these are defined for epidemiological homogeneity and geographical contiguity. So, but we need to look at those in terms of the tropics. So essentially what we've done is simply categorize those into two. And it's not a perfect fit, but it's a pretty good one. So these are the tropical regions of the world, and those are the countries that fit in it. So all the statistics I'm going to show you in the next couple of graphs essentially compare these green regions to these blue regions. So I admit that this is quite a complicated table, but there's you don't really need to understand any of the particular conditions here. You just need to understand the groupings, and you need to understand that this is the tropical table and this is the not tropical table. So this is the green area in our previous map, and this is the blue area. So in these two tables you have the three different categories of diseases, so the communicable ones, the non-communicable ones, and the injuries that we described earlier. And there are some things that I want to pull out to essentially reveal to you that the tropics are a unique place. So DALYs are not equal between these two regions. If you look at mortality on its own, the mortality burden is approximately the same in the tropical and non-tropical parts of the world, but we have a much more, so this is billion DALYs, so there's 1.56 billion disability adjusted life years in the tropics, so this is disease and death in one metric, and you can see from 1 to 20 here, this is the top 20 causes, and the number of the fraction of those related to each specific condition. Heart disease and stroke are the biggest mortality in both the tropics and the non-tropics, but when we start to look at this wider metric, DALYs, you'll see that essentially 12 of the top 20 causes here are communicable diseases, infectious diseases, and they're one of the things that we're most concerned about. And if you want to know why so many of us worry about malaria and neglected tropical diseases, you can see that they're top of the pops in terms of disability adjusted life years in the tropics. So just to ram that home a little bit more, what does that actually translate to into things that we can sort of take home messages, if you like? So the tropics, almost 50% of all the burden of disease in the tropics is a communicable disease one. And I guess what I'm trying to say here is that tropical medicine, even though we've been going for 100 years, remains a justifiable concept, and that these regions are unique in terms of both the burden of disease they have and the type of diseases that they have. So your mean age of death, if you're in the tropics, is still only 46 years compared to 65 from the not tropics. And the big differential, which we'll explore just a little bit more in a moment, is under 5 mortality. So 6 million per annum in tropical regions versus less than 1 million in tropical regions, in non-tropical regions. So before we get all completely depressed, and this is something that I really try and push home to our students, is that over my lifetime, which is roughly here, we have done fantastic things to under 5 mortality rates, and many of the people in this room can really take credit for being part of that. And it's this bit that I want to focus on here. So we've gone from 5 to 1 million under 5 deaths in the non-tropical parts of the world since 1970. And I think that's a fantastic achievement, and not one that is really that well known. And the point that I want to make with that is that we've done that with our existing suite of interventions. So there's no new magic bullets needed here. There's a huge amount of difference we can make with our existing suite. So one of the things I'd like to think about moving forward, and this line here is just taking this gradient. This is an entirely business as usual extrapolation of what we've done here. This will never be achieved, we'll never get to zero, but essentially what I like to do to frame our opportunity, as it were, what I and the society and all of us should be striving to do over the next 20 or so years is to look at what we can do to increase or decrease the gradient of that, to move this, to affect this potential burden in here moving forward. And I even think about that in terms of if we have a vaccine development line, for example, that doesn't bring a vaccine into about 2020, this is all that opportunity lost in that period. So it's a nice way to frame what we can do at the moment, and just remember that we did all of this with tools that we have now. So that's the global burden of disease, and that's the kind of, if you like, that's the space that we operate in. That's the kind of area that we want to influence, both as a society and as in our own little way as a research group. So how do we do that? Well, we spend a lot of time making maps, and I kind of want to explain to you why we do that and what the importance of that is for the global burden of disease. So why would we want to make a map in the first place? Well, we can use maps for a whole variety of things, and they can be very simply just advocacy. People like to know the distributions of disease and put them on glossy things to show to policymakers, and that shouldn't be underestimated. But we can use maps, and I hope to show you that as we move forward, as a very evidence-based spatial audit of current risk. And the thing that we're using maps more and more to do now is to use those as monitoring and evaluation tools, so they can establish baselines from which we can monitor change and measure impact. So that's essentially why we make maps. So the question then moves to, why do we want to make new maps? There are lots of them out there, we've all seen them. And this is where I get into builder mode again and say about how all the work done in the past really wasn't up to scratch. And this, to a good approximation, is true for most of the historical literature in cartography. There is no evidence base, or not one that you can go back and find. So, I mean, today it's a very standard thing to publish and make available all the information that goes into the map, but historically that never was the case. They also didn't benefit from all the modern computer, and GIS is geographic information systems, just a shorthand for computer-based cartography. And one of the things that we try to do now, which was never really done in the past, was to give you an idea of how uncertain or certain we are about certain predictions in the maps, because they vary enormously spatially. So we're going to talk a little bit about what maps we can make, what has been done, and what can be done. So infectious diseases, let's think a little bit more broadly now. So there are about 1,400 beasties, pathogens, ever recorded in human beings. And they may not be clinically significant, but that's about 1,400 that it's been documented a pathogen of some sort has been trying to make a living in a human being. Not all of those do that very frequently, and there are about 355 of those we counted up that are probably well known enough that they form parts of medical curricula, and that you would have if you're an extremely clever physician, you'd have at least a shooting chance of having come across them at some point in your teaching or training. So the question then we set ourselves is, well, of all of these conditions out there, should we map them all? Why don't we have a very good idea, or do we have a very good idea about their geographical distributions? So we set about thinking in a very much a landscape way, what actually do we need to know about any condition before we can map it? And there are a few obviously very, very basic things, but we went through and classified all of them according to these rules. So spatial things first. I mean, is the disease that we might be worried about, does it show any geographical dependence? And some of them don't. For example, Epstein-Barr virus, 80 to 90% prevalence in all human populations. So if you know, essentially if you know where the human population are, there's not a great rationale for mapping that. Etiology, do we understand the pathogen's life history? Well, we really do need to know a little bit about what's going on if we want to try and map something in any evidence-based way. And there are many of these 355 that, believe it or not, we still don't know how they work and what their life histories are. If we want to do any science, people need to measure things about the particular pathogen you're interested in. And if there aren't many of those measurements around, you're not really on a good starter. And utility is, of these 355, not all of them by any means are of public health interest. So essentially what we did is take those rules, put them through some decision trees, do a very rigorous systematic review of these 355, and the two people that spent most of the time doing that are in the audience, Catherine and David. And essentially what we found was that there were about 174 of these 355 conditions that we could map, and that only 7% of those had been. So I'm going to show you that as a kind of landscape of opportunity, if you like. So this is, you won't be able to read any of this, and we'll zoom in on it in a moment, but this is the 174 conditions that we think there is a very good rationale to map, both in terms of all the information out there, whether it's geographically variable, whether there's a public health interest in doing so or not. And just to show you that there are some obvious ones in there and some ones that are quite rarefied in that list of 174. And if we go back, what we then did is score every one of those. So if you have a black line here that goes from the center of the circle all the way to the edge, we think you've done enough of a job in terms of the data that was available and the mapping techniques that are available in relation to that particular disease. So that, for this one, it scores very, very highly. And the idea that you're supposed to get from this graphic is that essentially there's a massive landscape of opportunity to improve our geographical knowledge of these 174 conditions. So that's the landscape of opportunity for cartography, if you like. And what we're going to do now is talk about essentially how we do those maps, and we're going to do that with an example, our most recent example of dengue, and then we'll move on to say, well, we've done it for one disease here, how do we scale that up for an awful lot? And then essentially that's the end of the talk. So like an awful lot of epidemiology, we build on lots of hard work that's done by ecologists, and we're going to talk a little bit about ecological theory and how occurrence mapping works, but not a great deal about that because I don't have the time. We're going to talk about a little bit about dengue because that's the example that we're choosing here, one of the things that we've paid a lot of attention to as a research group. I'm going to go through these, evidence consensus, you'll hear more about all of these, occurrence points, pseudo-absence points, environmental and epidemiological covariates, and essentially how we make risk maps. And I'll do that in a very much a graphical way. And then I'll try and persuade you that these maps aren't just pretty surfaces and that we can do very useful things with them in relation to public health. So ecological theory, well, it's actually not a very difficult concept if you know what a concept of a niche is. So we assume that the observations we have of a particular disease approximate the realized niche of that pathogen. So essentially what that means is all the points of occurrences that we have, we're assuming in our analysis that from those we have a pretty good sample of where that disease occurs across the world. And then we're also making the next assumption that if we look at the environmental conditions of each one of those occurrence points, we can make a statistical model with which we can infer the probability of the disease occurring in a new location where we don't have data from that model. Now, again, we'll go into explore exactly how we do that, but you can almost guess from the outset that that's not a perfect, those are not a perfect set of assumptions by any means. And I kind of bring these out right from the start just to acknowledge the fact that we are aware of those assumptions, and as I talk through the way that we do these, we conduct this mapping, it will give you an idea that we're both cognizant of those and that we try very hard to minimize essentially the imperfection in our assumptions. So the first one is sampling. Do we capture enough of the spatial variation of any particular species, or in our case pathogen, to reliably describe its distribution? And then you might also think that there are lots of things, particularly with diseases, there are lots of reasons why a species or a disease might not occupy the full extent of the environment geographically that it's able to. Those would be biotic interactions, so for the ecologists among you, things like predation and competition. But they can also be biogeographical. A disease might just simply not have got to an area yet. And particularly with diseases, they can be because of human impact. If we're trying to map a disease that has a very big vaccination program, we clearly need to take that into account. Then there's also, in this step where we try and relate occurrence to covariates, we're also making the assumption that our covariate suite is representative of all the things that describe, or rather determine, the environmental space of a particular disease. And that may or may not be a good assumption. And we'll go through and talk about each of those in a moment, but essentially what we try to do is overcome the first one by getting as much data as we can. We try and overcome the second one by very crudely trying to understand the global distribution of the disease before we start. And we try and tackle the third one by essentially bringing our biological experience and our epidemiology to make the environmental data sets that we bring to bear on each disease very bespoke to that particular pathogen. So just before we go on to explore each of those in a bit more detail, why would we be interested in mapping dengue? Well, before we started, its global distribution was very uncertainly known, and its burden was sort of also a matter for a lot of conjecture. It's a mild to fatal disease with no cure, so there's nothing you can do about it once you get it. It's supportive care. It's also day-biting Aedes mosquitoes, so these vectors are very, very hard to avoid. Many of the things that you might be familiar with, like bed nets, for example, will do you no good. And control is extremely difficult. In temperate regions, this is a disease that's expanding. In tropical regions, this is a disease that is expanding massively. And even in countries like Singapore, which, if any of you have ever visited, is extremely an outlier in terms of the way that it conducts its control. Even Singapore can't get this disease under control. The reason for that is that the larvae and the adults thrive in urban areas, so everything that we do in terms of growers, populations, and we'll come back to this a little bit later, helps dengue. Its vectors spread readily on boats, its virus spreads readily in humans on aircraft. So very approximately, as malaria kind of recedes across the world, dengue is expanding. So it's one of those ones that we're very interested to essentially audit. So I'm going to talk, this is essentially the A, B, C, and D, and E that I just talked about by bullet points: evidence, consensus, occurrence points, pseudo-absence generation, our environmental covariates, and the risk map that we produce. So essentially we use these two things, the occurrence points and the evidence-based consensus, to make up some absence points, and I will explain that bit in a minute. We compare that with covariates, make a statistical model, and push out a risk map. So that is essentially what we do, and I'll go and explain each one of those in a little bit more detail. So evidence-based consensus, what on earth is that? Well, International Travel Health Guidelines, which is the acronym there, so before we started, disagreed on the endemic status of 34 territories. So those particular International Travel Health Guidelines are the WHO and the CDC books. And there are, just for those who are not familiar with GIS, there are about 270 to 280 territories in the world, depending on how you classify them. And there are about 100 countries on average, depending on whose estimates you take, that have dengue in the world. So the fact that two of our international organisations can disagree on quite so many countries lets you know kind of where we start. Ollie Brady in the audience is the person that did all of the work here. And essentially what we want to do and what we try and do with every one of our mapping diseases at the global extent now is do this very crude spatial approximation of where the disease is. And this gets rid of some of the problems in extrapolating to areas where we simply know for whatever reason the disease doesn't exist. So evidence-based consensus is certainly something that we do. And just so you can understand this map, if it's green, we're just absolutely certain that the disease doesn't occur there. If we're red, we're very certain that the disease does occur there. And if it's any of the colours in between, the evidence is conflicting. And not only can we use that to essentially constrain where we predict in the world, we can use these formally in the analysis as well. I won't go too much into that. The next thing is occurrence data, and this is a pretty boring slide, but I do want to emphasize the fact that historically all of this has been done manually. And essentially what we do is people within the group do literature researches in these types of things, and for those of you who are not familiar with that, there are large archives of scientific literature in relation to diseases which you can search. You can get all of those papers, you can read them, and you can work out where the disease was, and you can geoposition that, and you can do all of that manually. I kind of guess that you might understand that that's quite a labour-intensive process and takes an awful lot of time and an awful lot of people. And over a period of about 2 years, we managed to get about 8,000 points from 106 countries from dengue. I also bring up this because it was in the dengue maps that I'm going to show you in just a moment. We've also started to branch out and use other pieces of information, and a new collaboration for us was this group health map. We do accept data, again this comes up, but we're often challenged on this for as back as far as we can go, but I don't see that as the greatest problem in many of the things that we do. And just to reassure you, the vast majority of the data that we use to map occurrence is recent, so it's post-2000. So essentially we try and get as much information as we possibly can. This shows visually those statistics that I just outlined there, and the thing that you should essentially get from this map, and this will underscore the uncertainty metrics that are important to always see with your maps, is that we're actually very data poor in Africa, and this will be a focus of future research for us. I'm going to skip over this one, but if you do want to make any niche modelers slightly uncomfortable, this is the sort of area to start asking questions about. And the fact is that we don't ever usually record in the literature when we don't find something. So there are all kinds of dark arts around essentially making up data in niche mapping. It's not something unique to what we've done. And the way that we get over some of those assumptions is just an ensemble through a whole range of assumptions that we can make there and take average products. I didn't want to gloss over that fact because it is something that we spend a lot of time thinking about and trying to get right. Environmental data sets, so these are all the things that we then try and stack up on the right hand side to say, well, what do we think is determining the distribution of all those occurrence points, and so what can we start to build a statistical model from. You'll be very familiar with things like climatology, so this is a map of global rainfall, very little rainfall here, up to almost a metre per month in various parts of the world. And you'll pretty much be familiar with the fact that we can get those information from lots of places. I show you the next one. This isn't just temperature. When we know about a specific disease and have a lot of experimental work done, which we do for dengue, you can actually start to transform your meteorological variables into things that are a little bit more, we hope, biologically relevant. So this is some work that Ollie's leading in our group, and it's the essentially we change temperature into daily dengue transmission suitability based on that and some experiments that have been done. And the point essentially is that we do make a lot of effort to try and choose very carefully the environmental data sets that we throw in. We don't just take everything that we can throw at the analysis. And although you'll be familiar with things like rainfall and temperature, we can put in any kind of covariate, and this is a more recent one, and I show you this. This is a pixel-based gross domestic product, and you'll know that many other things affect the outcomes of diseases, so those are available to us in the analysis, and this is another one of them. I don't have a lot of time to talk about boosted regression trees and some of the methods that we use. But this is, after going through all of that process, this is the map that we generate. And anybody in this business will be able to give you very good metrics of the statistical accuracy with which they make those predictions. So don't trust those for a minute. If you see a bad statistics on the map, then you really should be wary of it. But we like to use 3 different things to essentially test how well we're doing. So statistical accuracy is one thing, and what we can do is, of course, drop out certain fractions of data, redo the map, and see how well we're predicting the things that we already know, and that would be the standard way to do it. But we also can look at geographical plausibility. Is this map, we can show it to lots of experts, does it do what we expect it to do? Is it giving us a good description of our definitive extent, the map that Ollie made, that I just showed you, and the occurrence data that we've collected. And the other thing that makes us particularly reassured when we make a map is if the covariates that it selects to make that map are epidemiologically relevant. And the three that I just showed you weren't a random selection, they happened to be the three that came out as the biggest predictors of dengue in this mapping process. And that, all of that together helps us improve the faith, if you like, or our rigour with which we can stand by a particular map. So I'm going to be told off by our journal editor here for not labelling my axes appropriately, but essentially you don't really need to know too much about these. This is the metric, this is the probability of occurrence that we predict here, and if we have a whole series of cohort studies, so this is where people will go out and measure over a year a very defined community and the amount of disease that they get, and we can geoposition those on the map, and we have an incidence rate. We can define a relationship between the probability of occurrence of the disease and incidence, and we can use that to make burden estimates. And that's exactly what we did for dengue. Dengue comes in two flavours, really. There's apparent infections, so those are infections that have an effect on you that's significant enough to stop you going to school or going to work, and many, many inapparent infections as well. And these are what these two different graphs show. And then we can start to total those up with population services for 2010, and we can make consistent global estimates in a way that had never been done. And this is just to reinforce the fact as to why maps are useful. The Bill and Melinda Gates Foundation is already using these figures to evaluate the position of dengue in its portfolio of activities. Gavi is doing the same thing, should a dengue vaccine ever become available. And a recent development is all that the surfaces that we start to make will also now start feeding back into the Global Burden of Disease 2013. So these maps will then go into covariates to help those predictions moving forward. So one of the problems with the Global Burden of Disease is that its iterations are only every 5 years. So that is moving to an annual basis now. And one of the things that they really want to help in moving that forward is to have covariates for this. So that's one of the motivations for the ambition that we'll talk about in a moment. So one of the things that's important for me to do is acknowledge the fact that none of this is done on my own. This is a large group of international collaborators that help us do this research, and I just want to call that out there. Sam, the first author of this, is in the audience, and if I haven't communicated what we did in that particular article sufficiently well, it's there for you to read. So that took us, quite a few of us, essentially about 2 years to complete. And if we go back to thinking about how we might scale up for the future, I'm going to restate the problem set there. So that's two years, approximately 5 or 6 people employed in that project. You'll see, in terms of leverage time, a massive contribution. So how on earth would we be able to scale up that kind of activity for these 174 diseases that we think should be mapped? So this is why I want to take our group moving forward and essentially challenge us with the ambition of making a global atlas of all of these infectious diseases. So try and think through how we might go about doing that, and that's what we're going to spend the rest of our time devoted to. We're going to talk about the data sets that we can harvest to make available for that. We're going to come across terms about big data and big signal, and we're going to also talk about how we might automate many of the things that we do. And I might slip into this term, so I'll talk about the acronym from the start. So it's our description for this whole enterprise, this whole process, and it's Atlas of Baseline Risk Assessment for Infectious Diseases. So if I start talking about a braid, that's what I mean. It's this whole concept of, can we make a global atlas for infectious diseases? So if we think about the first part of that process, is where do we actually get all our occurrence data from in the first place? Well, we manually look at things like PubMed, and very rarely, funnily enough, do people look at GenBank historically. And essentially all I want to do with this slide is to let you know that there are resources out there that we just really don't utilize to their full extent. So PubMed has about 21 million entries, and from various sort of tests that we've done, we think there are well over 500,000 decent occurrence points that could be brought to bear on at least 168 of our 174 diseases. I won't read out all the same numbers for GenBank, but you get the idea. There are lots and lots of high provenance, and what I mean by high provenance is that they're very well documented occurrences of a particular disease. So if you've got an entry on GenBank, which is its genetic sequence, it's highly likely to be the disease that you're worried about. One of the things that people, when we start to talk about GenBank for risk mapping, that they always say is, well, GenBank will only have, nobody geopositions it. Well, in fact, already 13% of entries in GenBank are already geopositioned. And this map here just shows you an approximate, if you add up all of those entries, and Sam did this one, it has a very good global distribution already. So it's a much underutilized resource, and one of the ones that we'll be moving forward with. Web reporting systems, these are also really not used, and I need to thank John Brownstein and Nigel Collier here, who run HealthMap and Biocaster respectively. So they're on board with the braid, they're new collaborators of ours, and their archive doesn't go back as far. They both started in about 2006. And what they do is they host websites like this that essentially alert people to any outbreaks of particular diseases, and you can see that they cover quite a few of these respectively, and that there are accumulating very big archives of occurrence points which they can make available. And when we have looked at their back catalogue, we see that they've got a lot of things that we can already use. So now we get on to some of the more social media type things, and this is where I think this could be potentially very, very transformative for all of the things that we do. And I know there'll be some doubters out here, so I'm going to take some time over this slide. And Twitter is the one that I'd like you to think about, although it's not an exclusive, don't think of it as the only example. I think Twitter is there. It's going to be all in our share portfolios fairly soon, I imagine. But it's one among many, and I think it's an area to keep an eye on. Already, and these statistics, it's growing so fast that these statistics I've updated about 2 or 3 times over the generation of this talk, and it's somewhere more than 150 million tweets a day, and that's increasing exponentially. 5% of these are already geopositioned, and I'll show you this movie in a minute. And the assumption, which I think is a fairly safe one, is that there is a huge amount of disease-relevant data in here that we can use. And I'll play a movie, which is a very, it just runs for 7 hours, and I would encourage anyone to play around with this website, TweetPing. You can get a very quick idea about where people are tweeting in the world, and I'll show you that in a second. But the other thing that I do want to emphasize with this social media is and this is a thing that I don't think is very well documented now, is it's two-way. So if somebody starts tweeting an awful lot about a particular disease in a particular location, there's nothing to stop us automating tweets back to them and trying to find out the provenance of that information. And that's the bit that tends to be forgotten in some of this. So a huge amount of data, and we'll have a look at that in a second. So this movie here is TweetPing. So this is 7 hours displayed in, I'm not sure how many seconds it goes on. And the things that I want to, so this is a subsample of what everybody's tweeting for everything around the world. We've done the experiments to see, essentially for our 174 diseases, what people are tweeting about. and there are lots of disease-related tweets around the world. But the take-home message for this, remember this is only 7 hours and it gets up to many hundreds of thousands of tweets already, is that you're perhaps the stereotype that you would have come in with is that it would only be Europe and North America and a few countries like that that are tweeting. Well, it's evidently not the case. Indonesia is the second biggest tweeter in the world, and Iqbal, I'm not sure if you're out there, you can explain to us why that is later. But all around the world, in many of the areas that we're interested in infectious diseases, people are extremely active in social media. So don't come with that prejudice that it's not something that we can get lots of information comprehensively and globally. I'll acknowledge that there are certain areas of the world that we might always be having an uphill battle, but that wouldn't just be unique to social media. So this is one thing that we think moving forward will be very important to us, and this is essentially just grabbing as much information as we can. And if you start to talk about big data, and I'd like to prefer to use the term big signal, where can we get the most useful information, people start to use these V words, which get me very confused: volume, veracity, volume and velocity, in relation to types of data. But essentially what they mean is how much of it is there already, what's the archive, what's its provenance, how can we trust in that information, how quickly is it updated, and how timely is it. And just to bring this home, I think that our social media, nobody really archives many of the tweets at the moment. At least in a way that's available to us. I'm sure there's particular companies that have very big archives of those. The veracity there, I mean, there is a huge amount of information that we'll want to discard there, and a huge amount of chaff. I accept that right from the outset. But you can't argue that its volume is impressive and its timeliness it cannot be surpassed by anything else. And if you contrast that to our more traditional sources, and even these we underutilise, it's essentially a mirror image in many of the things that we would be interested in. And I think web reports come sort of somewhere in the middle of all of those. So essentially, in the nutshell, the idea of a braid is to use all of those things together and use the wonderful archives that we have here a little better, to help triage some of the information that we use here, and to certainly get the signal from this. But you'll know that that's not very timely, but this is. And the whole concept is bringing all of the strengths of some parts of this data stream together to get much better, timely occurrence data with which to feed this process. So you've seen this graphic before, and that's the risk mapping. And the next thing, the next concept of a braid to try and articulate to you all is that don't think of this as a static product anymore. This arrow is extremely important, and the notion that we would try to sell with a braid, and the notion that we think will start to move things forward, is that this should be thought of as not a static map, but one that continually evolves. So if we essentially automate this process, we should be able to iterate. Not only should we be able to make one map for all of these diseases, we should be able to make a live map for all of these, and it should be continually updated. So a little bit more detail on about how we might want to do that. So the first of it is we need to take humans out of the link of reading all of these abstracts. And you might think, well, how on earth do you do that? But this is what web reporting systems already do. So they have very advanced machine learning to look at both the provenance of the information and to automatically geoposition it. So that's something we want to leverage, and we want to use that information and bring it in and essentially use all of the wonderful archives in PubMed and ProMed, which are freely available to us, to rapidly increase the information content with which we're trying to map all infectious diseases. We can automate the mapping. That's actually not a particularly hard thing to do. We adopt a technique called boosted regression trees for a whole host of reasons, but there are many techniques that you could use here to automate this mapping, and that's essentially just a programming problem. One of the things that we're very committed to doing is also using much more novel techniques to try and look at the validation in terms of a braid. So if you imagine you've got 174 conditions that you're trying to look at, and you're iterating those perhaps on a weekly basis, you really do need to bring in the crowds to start helping you look at those maps. And we do believe that public health, and you will have seen many of the crowdsourcing projects around the university, we think public health will be a big draw. And essentially we will want to sort of syndicate our maps out to as many people as possible and get them to validate our predictions in different parts of the world. And one of the ways that we'll do that is with a thing called a GeoWiki. So you'll all come across Wikipedia and editable text in relation to dictionaries, where you can actually do the same things with maps, and they've done it in relation to land cover. So you can get a map of what we might, for any location in the world, and we have predicted that you have a higher occurrence for this, that and the other disease. You can log in and you can say, well, we think that's good, bad or indifferent. And if we do this properly, we can start to rank all of our people that do the crowdsourcing as well. So there's very nice ways that you can get feedback loops into here as well. And we hope to partner with Trudy's group here, the Global Health Network, to essentially, that we'll have pre-organized user groups into relations to many of the diseases that we're worried about. And finally, of those 174, clearly there'll be quite a gradient in those that have public health interest, and those that are really very important to us to nail. So those that, for example, are in the top 20 of the global burden of disease, we will start to bring together expert panels of arbiters. So I do also need to say, why on earth would we do this? So convince you a bit of the audiences here. We're not just stamp collectors. We don't want to make a glossy atlas, but that is actually one thing I would like to see in the next 5 to 10 years. But it's a spatial audit. It's essentially auditing that whole spectrum of infectious diseases, and we can use those for advocacy. We can use those for tracking change. And I think we can also do a much better job than we currently do in advising in relation to travel health. The Global Burden of Disease programme will be a major partner in this moving forward. So we'll start to supply those with covariates for as many of these infectious disease conditions as we can. And of course we can help them improve the timeliness of that if we can update and automatically update those conditions moving forward. Depending on how successful we are in this first phase, I think biosurveillance is not too big an ambition either. And I would just like you to think about the fact that how on earth do you, if we really don't know, which we don't, as I showed to you for many, many of these infectious diseases, how on earth do we know if something's unusual, an outbreak is unusual in space, if we don't really have a really good idea at the moment about what its natural niche is? And I would say that that's true for many of the conditions that we might be worried about. So I have almost used up my time, but you'll be glad to know we're on the we're on the home stretch here. And we also need to think about the future. So one of the things that we are often tasked to do with our maps is to look at them and try and infer what things are going to change. Now, this is a horrible ask, and the literature is actually... I had a few of these quotes, but then I took them out because I thought they were too mean. But there are essentially lots of people on record as to saying things like we will all be starving in the UK by the year 2000 because of population growth. And this is not the type of predictions that we want to do. But I just want to, in this sort of overview talk, highlight a few things that I think are going to be very important epidemiologically and that we should strive to keep an eye on. I don't dismiss climate change or biodiversity loss here, but you will have heard an awful lot about those, and I don't have an infinite amount of time, so I'm going to focus on these ones here. And the first one is population. So many of you will be familiar with these types of graphs here. So this is time again, and this is approximately, well, this one is exactly, so what's the data? No, this is approximately like my lifespan. So we're about 7 billion people today, and we're going to go to plateau at about 10 billion. People argue about that, somewhere between 9 and 11, but there is an end in sight, and that plateauing people predict will be in about 2050. Tropical populations, and this is sort of starting to come back and get us back to the Royal Society's aims and objectives and thinking about the tropics and what particularly might be problems there, is the tropical population exceeded the non-tropical population in 2007. So there's already more people in that part of the world. And these maps here, essentially this is a population map of the world, and you just total up population by latitude or longitude, and it does start to give you an idea of essentially where all the people are. It's slightly north of the equator here, and all in the east. So that's where all the people are now. If you look at where all the population growth will be, so it's this part of the graph that you're looking at in the future. This is our temperate part of the world, not a great deal of change here. So all of those new people will be in those tropical parts of the world, subject to many of those infectious diseases that we've talked about earlier in the talk. So the point here is essentially global population is a big feature for the globe, but it's particularly an issue in the tropics, and it will have big epidemiological impacts, not least because we just have that many more people to deal with. This I have to credit Marius Gilbert, who I think is in the audience, and this is something that I hadn't ever really thought about until recently. But humans, in terms of, so the axes here are essential host biomass. So if we think about us and the environment as from a pathogen's perspective, we're just walking things that could be infected. And essentially the biomass of those is a good indication of how they're stratified. And in fact, it's our livestock that present the biggest opportunity for many of our diseases. And this, I don't think many of us appreciate. Of course, many of the diseases that we're worried about, of those 174, have a link to wildlife either explicitly as a zoonosis or... That shows me my time's up, but we're very close. And it's essentially as well just to bring home the point that the changes in the way that we feed ourselves are going to be extremely important. And again, just to bring home the notion that that's not really going to change. I don't have figures for the future here, but you can see that we've kind of stabilized in the temperate parts of the world, but it's the tropics that are having the big growth in the livestock there. So the opportunities for pathogens, it's not just humans, but all the things that we rear to feed ourselves are growing massively as well. I should have pointed out that these little thumbnail map here just reminds you of the tropics versus the non-tropics that we're considering. Global energy consumption, well, this is, we might reassure ourselves that population is plateauing in about 2050. Well, these data show that there's actually no plateau in consumption predicted by anybody. In fact, I'm going to say that this is one of the things that I worry about even more than population growth. It's our unbelievable capacity to essentially use energy. So again, if we look at this axis here, again, approximately my lifespan, this is billion of tons of oil equivalent. We've gone from 3 to 12 billion tons over this duration, and we're projected to increase to about 18 billion tons equivalent in 2040. And there are various sources for these figures. But again, this is a kind of reversal of, this is a reversal of fortunes in relation to the tropics. So they get a very small fraction of that energy moving forward, and we dominate it in our part of the world. And again, I think that's a really important thing to us to factor in when we try and think about how the world might change in the tropics. Finally, transport, and I just pick out the global air network here, and this, if you were fortunate enough to be born in 1933, were all the international flights that you could take at that particular time. And they're even hard to pick out. There's a few here, and they come from this particular book here. So there's nothing new in the world. So back in 1933, we were talking about epidemiology in relation to air travel. But just to sort of drive that home, how much that's changed today, if you want to travel around the world now, you can do it much more effectively. And the backdrop there was our dengue map. So you can see that dengue has also spread in that time. So the notion here to get across is that tropics aren't isolated. We are a very, very connected world, and that connection is increasing. And again, just to come back to the notion of population, That circle there is an interesting one in that more people live inside that than outside of it. And I think when you start to, I would love to be able to put one of the livestock as well over that, but I don't have that information. So Marius, maybe if you could provide that for me, that would be great. But it's just an idea to think about the world is essentially very skewed, and that these are some of the factors I think we will have to bear in mind as we're making cartographies moving forward. All of these things will effectively intervene with the distributions and the realised niches of the pathogens that we're trying to predict. So you'll be glad to know that we're almost there. So my conclusions are, we've talked a little bit about the society, and I hope that I've managed to let you know that it's got a glorious history, and I do hope that it has a glorious history, a glorious future, and I'll try and be part of that. I've also tried to highlight the global burden of disease for you, and you'll have seen that although we've done a lot, so I don't think we need to be too depressed about the state of the world at the moment. We do have a lot still to do, and that is really a problem of the tropics, and that problem of the tropics is one of infectious diseases. I've also talked about the history of our mapping, and essentially tried to say that that was both poor in the way that it was done and in the diversity of things that were done. I've tried to argue that the way that we map things now is at least richer in kind, but it's very poor in extent. We haven't really addressed the landscape of infectious diseases that we could. And I've also tried to say that in the future I hope we can both be rich in kind and in extent, so that with the notion of a braid, which we are fairly optimistic about getting funded, but I can't talk about that anymore, that we'll be able to rapidly improve our knowledge in that space. I've also then tried to talk about some of the things that I think will be important for us as a group and a community to think about in the future in relation to tropical disease. And if you will indulge me just for my final acknowledgement slide, it is one of those chances, those rare chances that you get to thank people. And what I do want to do is thank my family who are here for their support over the years, and particularly my wife, wherever she is, just down there. And I also would like to do the more traditional thing of thanking my department, the Department of Zoology. And it was when you start to get reflective and do these talks, I realised that I will have been with you for 20 years in October. And I would like to pick out very particularly David Rogers, Sarah Randolph, Willie Wint and Sunetra Gupta, who particularly at the early stages of my career were all fantastically generous with their time. And that's really important for young scientists, and I just hope I can do as well as the example that you've set. I would also like to thank the Wellcome Trust, and again, getting a bit reflective, you allow me to do what I think is one of the most privileged jobs in the world, and you've allowed me to do that for 15 years. Long may it continue. I would like to thank St John's College, who have welcomed me very recently, and for all of their help in arranging today. And also the Royal Society of Tropical Medicine and Hygiene for their faith in me, and I hope to earn that over the next couple of years. I'd also like to thank my lab. They make going to work always an experience. And I would also like to thank everybody listed there. I won't, who have helped enormously with lots of the figures and graphics and put up with me over the last couple of months in putting all these maps together. So that's it. I'm going to leave you with that, other than to say that one of the most important things that we need to do as a society is get lots of people to attend our meetings. And our next one is about this time next year. It will be devoted to measuring progress, and it's in Oxford Town Hall. And it will be about measuring progress not just epidemiologically, so not just in terms of scientists, but we want to bring in a much wider range of communities, scientists, non-government organisations, funding bodies even, and challenge them to look at what they do, how they evaluate themselves day to day, and really how we can improve the way that we conduct business in relation to public health more widely than just our scientific impact. And of course I have a newfound interest in this, in just starting with the Royal Society of Tropical Medicine and Hygiene and thinking about how after 2 years I'm going to get up and be able to justify to you that I've done a good job or not. So with that, thank you very much for your time and attention, and shall we have some wine?